please draw a graph through it all so that you end up with this information get back at the root. This takes some work. LDNS keeps thinking it can go off and talk to the network. I want to just use the key material that I gave it, or throw it all away. So I'm still working on it. Nothing really I can do. But you know what's a totally different option? Well, you could just be Google's Adam Langley. Who's Adam Langley? Well, Adam Langley is one of the engineers working on Chrome. You know what I got this morning? I got access to a custom private build of Google Chrome with DNSSEC embedded. Yes. So here we have a site, and this site's online now, dnssecexp.org. The lock is there, the text is green. When you look at the cert, there is in fact DNSSEC material embedded. Now, I want to give a caveat. This is an unofficial private build of Chrome. Google is not at all committed to DNSSEC, DKI, or X.509 certificate embedding. This is just Adam and I seeing what's possible. That being said, this is awesome. Google Chrome, DNSSEC, yes. And now I think it's good to start talking about actual applications. So where do we start with implementing domain key infrastructure? Well, we started this talk with Phreeload. Phreeload is federated identity for OpenSSH. It is based on the idea that you shouldn't log into a server with your public key. Your public key is a mass of random bits. You should be able to log in with your identity, or at least your email address. What ends up happening is the authorizer, in this case a text file called authorized keys 2, but it could actually be an LDAP backend as implemented by FedSSH. What happens is the server knows, okay, here's an account. Let's see who's allowed to come in. Okay, you're claiming that you might be one of these users that's trying to come in. It will look up in DNS the actual public key that you're supposed to use to get in. And how does it know that this public key it looks up is actually yours? It's able to simply check the flag. By the way, when I did the end-to-end resolve, when I went ahead and directly got the key material for this SSH public key, did it chain back to root? Not did I ask anyone else, not did I hope for the best. When I got the key material, does it say, this is in fact dan@remotesupport.org's key? Is it him? If so, I let him in. If not, I say no. This was built in a couple of hours. This was not complicated. Guys, we have been suffering through broken federation systems as an industry. Everyone here might not know what federation is. So let me actually explain that as well. Grammar. So there are thousands, tens of thousands, hundreds of thousands, millions of organizations in the world. The old model of how computer people thought the world worked is all you need to do is talk to people inside your own organization. You know who's not inside your organization? Customers, or suppliers, or business partners, or vendors, or contractors, or temp agencies. When you're a company, that which is inside and that which is outside can get kind of blurry. It's just the way it is. And so one of the things we need is the ability to operate across organizational boundaries. Now note, email just works fine. Have you ever been on those threads where everyone ostensibly works for the same company, but there's like 20 different email addresses at the end of everyone? It just works, right? Why? Because email is fully federated, meaning it operates across organizational boundaries without a care, because everything chains back to the same root. Now you want to encrypt anything and things go to heck because we have no key material. But you want to just send messages, it works. Federation at its core is about being able to interoperate and interact with identities outside your organization. When I showed you that SSH demo at the beginning, what I was showing you is there's a customer, and he's got a network, and he's got a device on that network. And that device on that network has no idea who you are as Dan, or as Bob, or as Jim. It doesn't even know who this remotesupport.org company is. But you know what it knows? It knows, hey, I got to trust someone from there, and I can go to DNS to find out if I'm actually speaking to them. Done. This did not take a lot of work to implement, but it is actually fairly revolutionary. Here's why. There are 3 choices in normal federated systems. The first choice is called end-to-end complexity. This means is every company needs to do explicit negotiation with every other company to figure out just how much access they're going to give each other to information. And it's miserable. It's utterly miserable. It is very expensive. And it leads to a very precise outcome. I believe that if you're going to make claims like I've been making, you have to be able to show examples. On Gmail, if you receive mail from PayPal or eBay, the email looks different. Well, that's nice. That's 3 companies that have a relationship. That's about as far as our present-day technology has been able to get us to scale. End-to-end complexity got us 2 to 1. How do we get the rest? Well, the next option is the risk of kingmakers. In kingmakers, one group is trusted by others as the identity manager, and everyone's got to hope that guy doesn't turn into a crazy taskmaster. Give you a hint. He always turns into a crazy taskmaster. Final thing is what's called key bleed. This is what's happened with the certificate authority system. Effectively, there's a bunch of people with equal powers over assigning keys. One guy wants an advantage over the rest, the security level drops little. Now one guy wants an advantage over what's remaining, security level drops little. It's a race to the bottom. Whether or not people have the best of intentions, give it 15 years and it's going to be broken. So that's kind of how federation has been failing us thus far. What is interesting in DNS, what is interesting in DNSSEC having a root is we have a 4th model. We refer to it as the silent overseer. ICANN is a very interesting organization. And by interesting, I mean totally and utterly constrained by a huge number of external political constraints and actual straightforward technical limitations on what they're able to do. Now that's not saying they can't do anything, because they can and have done tremendous things. Like, for example, shepherding the actual root getting signed. But if you compare the powers of the normal master roots out there, and then ICANN, man, I know which one I want to have to worry about. I'm going to worry about the guys who can't act to hurt me. So that's what's interesting. That's what makes domain key infrastructure so powerful. It is federation that will actually work. So what do we do? Do we add LDNS or libunbound to every package out there one by one? Oh, you know, eventually, possibly. Maybe the operating systems will actually give us some functionality, give us some inherent caching. But what do we do in the short term? I don't want to write patches for everything. On Linux and Unix, SSL is handled via OpenSSL. And OpenSSL has a single function called X.509 verify cert. That is a nice and self-contained library call. One function, one position. This is what says whether an SSL connection has been accepted or not. Could we do something with that? Yeah. We can build something called Phreeload. Phreeload is a DNSSEC verification engine that can actually be applied with no code modifications to pretty much every app on Linux and Unix through the LD preload functionality. There is prior work here. Russ Mundy at Sparta has done some tremendous work with LD preload using what he calls libval-shim. Excuse me. There it is, libval-shim. Libval-shim also goes ahead and runs in front of applications and says, oh, you're doing stuff, let me DNSSEC that for you. But what libval-shim does is it DNSSECizes the DNSSEC operations. So when it looks up an address, when it looks up a text record or this or that. And so you can get a lot of assurance that the addresses you look up are safe, the IPs. There's lots of ways that IP addresses can be manipulated. I think 13 was the last count. It's a kind of an exercise you do with the kids learning security. Talk about all the ways to hijack an IP address. Very cool work for its time. The other thing that it did was Mundy's work was done assuming that the root would never be signed. Because frankly, for quite some time, it looked like the root would never be signed. So it doesn't do all the chasing and tracing and complicated stuff. It just says, I assume if I'm looking at foo.com, I know how to recognize foo.com. Phreeload is different. First of all, it does chasing. And second of all, it operates at the precise layer for the precise applications that are attempting to achieve end-to-end trust. It hooks SSL, not DNS. And it says, we're going to make sure that if an application is trying to make a secure connection, that what it speaks to, that the certificate validation process goes through a DNSSEC validation path. So, what does this look like? Here's curl without Phreeload. Curl is going to go ahead and it's going to try to connect to https://hospitallink.org, and curl is going to vomit a huge amount of error messages at the screen, and the last thing the user sees is the last line that says, use the -K or -- insecure option. Because one option for turning off certificate validation wasn't enough for users. They had to have two to make sure the user didn't send a complaint mail. Okay, so that's lame. You know what would be awesome? If you could just put the fingerprint of the SSL certificate in DNS, and now when you connect to hospitallink.org, the fingerprint is looked up and it says, oh wait, this certificate I see, it may be self-signed, it may not go to any certificate authority, but DNSSEC is cool with it. What does that look like? That looks like this. Curl HTTPS, hospitallink.org, and this is the story all about how my life got twisted upside down. So, but just to be sure, so you can see that this is actually working, if you export the variable DNSSEC debug equals 1, you will actually get a bunch of debug symbols or debug messages put out showing you the library interposing itself and injecting DNSSEC validation. If you go ahead, now what the schema is now, this is deliberately incorrect. There's a whole bunch of work from a whole bunch of people to figure out the exact right way to put that hash, this figure. So the deal is you have a certificate. When you summarize it, you get a fingerprint or a thumbprint, and it looks sort of like this. The question is, I can go ahead and for any name, I can get a value out. What is the best name to get the best value out? There are a bunch of ideas, but I don't want to go ahead and step on some people's toes, so just accept this is the wrong way. So, if we go ahead and we break the actual thing loaded in DNS, just to demonstrate, what we see in curl is curl stops working. Even though it's doing a lookup in DNS, the wrong signature came back, and therefore it is rejected. How cool is that? Now when we fix it, curl works. You know what else works? wget works. You know what else works? Postfix, Postgres. You want to do secure database-to-database communication? MySQL. Apache. Why would Apache be interesting? Well, there are these things called client certificates. In client certificates, the server does not authenticate you. You authenticate yourself to the server. Now, client certificates haven't worked very well ever since they came out. And the major reason why is, how does a client certificate, which by the way might live on a smart card, how does a client certificate you get from one site work on another site? Well, this is a classic federation problem, and federation has been a disaster. Now it's very easy. You just look at the name you're offered. It's like, oh, you claim to be Dan at recursion.com or recursion.org for now. Let's go to recursion.org.